Hello, I'm Dr. Bill Crofts from the University of Warwick, and I'm a director of the Warwick Satellite Engineering Programme, WUSAT. This presentation is to tell you about our current satellite mission, WUSAT-3. The first slide shows the concept of WUSAT-3 being launched to the International Space Station, where it will be placed into a low Earth orbit in order to begin its operation. This presentation will look at the WUSAT-3 mission, i.e. what is its main technical purpose. We will give a simple explanation of WUSAT-3's payload, i.e. what instrument is it carrying, how does it basically work, and why is that important to the mission. We will also look at WUSAT-3's platform, that is the main body of the satellite itself, and what must it do to enable the payload instrument to operate properly. Finally, we will tell you about our WUSAT team and why so many people play their part in making this happen. The main aim of the WUSAT-3 mission is to test a novel method of being able to track tagged wildlife from space. We won't be tagging any wildlife ourselves in order to do this, but we hope to test a system that could bring many benefits to those researchers and conservationists who are keen to preserve wildlife and protect the range of biodiversity on our planet. You may often have seen wildlife programs where animals carrying radio tags are tracked by researchers carrying aerials in order to determine where the tagged animal is. Of course, that means that they physically have to go to the area where they suspect the animal is at that moment. This is not only highly inconvenient, but is often not possible due to terrain or even political difficulties in some countries. There are already some systems in use that use satellites to track wildlife. However, this slide shows one of the main drawbacks to current space technology commonly in use. Current satellite systems require the tag to monitor the animal's movement by recording GPS data of the animal's position at regular intervals. When a monitoring satellite then passes overhead, it will then signal the tag to transmit its recorded data up to the satellite. The satellite will store this information for each tag and then download the data when it passes over a ground receiving station. The main problem is that the tags are large and heavy. In order to record GPS data, like a sat-nav, and then have the power to transmit all of the data up to an orbiting satellite, this limits how much the size and weight of the tag can be reduced. The size and weight of GPS wildlife tags also limits the range of wildlife that can be tagged in order to monitor their movement patterns. With birds in particular, there is a great deal of interest in being able to monitor smaller bird species who currently can't be tagged for monitoring in this way. This short video shows how it is possible to trace the pattern of a larger species of bird carrying a GPS tag during its migration from Central Europe. Let's now see how WUSAT-3 hopes to test a different method of monitoring wildlife tags and proving a technology that may allow the tags to be smaller and lighter. This slide shows the basic life cycle of WUSAT-3. It is being designed for launch to the International Space Station. From there, it will be deployed into a low Earth orbit of approximately 400 kilometers altitude. Once in orbit, it will complete a number of procedures that will prepare the satellite for operation. It will then aim to detect the signal from tag-type transmitters that we will place in known locations on the Earth. I will show you later how this method can allow smaller, lighter tags. The collected data will be transmitted to a receiving ground station At the end of its operational life, we will aim to ensure that WUSAT-3 rapidly descends from orbit and burns up in the upper atmosphere so that it doesn't add to space debris in orbit. This slide shows the main external features of WUSAT-3's payload. One face of the satellite has 4 antenna patches arranged in a precise pattern. There is also a hole that is the viewing aperture for an internal camera. This side of WUSAT-3 must be controlled to point towards Earth and be as stable as possible. An imaginary line taken from the satellite's orbit position to the center of the Earth will pass through the Earth's surface at a point called the nadir. Hence, the payload face of WUSAT-3 is nadir pointing. Imagine that when WUSAT-3 is passing over Central Europe, for example, it detects the radio signal from a tag. This simple signal is not transmitting any locational data like a GPS tag. It is simply transmitting a basic signal that includes the tag's identity. Once this is received on WUSAT-3, the camera is triggered to take an image of that part of the Earth's surface below. At the same time, the tag signal is being received by all 4 antenna patches, and the signal on each patch displays a slight variation or offset due to the difference in the position of the antenna patches. This offset information can be used in conjunction with the image in order to estimate the location of the signal source within the image. This is indicated on the slide by the yellow arrows that represent the antenna offset information that will give an estimate of where on the image the source of the signal is. Much of this processing can be completed on the ground, provided the image and antenna data are transmitted to a ground station. Once the image and antenna data have been processed in order to estimate the position of the signal source on the image can then be overlaid or registered onto an image of an actual map. This will then allow the signal source position on the image to be directly translated to an actual geographical location of the tag on the map. Suitable computer programs can do all of this processing quite rapidly. It should be noted that in many cases, very high accuracy of the wildlife tag location is not required, providing an overall pattern of movement can be monitored. The key point with this technique is that the tag could be smaller than a small car key fob. All of the data acquisition regarding location is accomplished through WUSAT-3's payload arrangement and the later processing of the data. The job of transmitting large amounts of data is from the satellite to the ground station rather than the tag to the satellite. Hence, the tag should be able to be much smaller and lighter. The WUSAT-3 platform is the basic chassis and operating systems that will make the satellite meet the needs of the test payload. The 2019-20 WUSAT team compiled a lot of information on all of the components and subsystems being used and produced a configuration model to determine where and how everything would be arranged and mounted. This will now be developed into a fully operational engineering model that will be rigorously tested. If these tests satisfy a European Space Agency review panel, we will then get the go-ahead to build the final flight model. WUSAT-3 is being designed for a launch to the International Space Station via a European Space Agency launch program. This requires WUSAT-3 to meet the requirements of an American deployment system called NanoRacks. You will see this on the next slide. However, there are options either for a launch to the ISS or a launch that puts WUSAT-3 directly into low Earth orbit. We may not know exactly what sort of launch we will be on until later in the program. Once the WUSAT-3 flight model is approved and shipped to the launch site, it will be installed into the NanoRacks deployment unit and made ready for launch to the International Space Station. Here we see astronauts on board the ISS who are loading NanoRacks deployment units into the deployment carrier that will take the NanoRacks tubes outside of the ISS through an airlock. This shows an image of the NanoRacks deployment unit that has passed through the airlock and is in position to deploy the satellites into low Earth orbit once the command is given. You may just be able to see the gates on one of the tubes is already open, ready for deployment. When WUSAT-3 is deployed into orbit from the ISS, it must remain mostly in a sort of sleep mode for at least 30 minutes until it is well clear of the ISS. Certainly there must be no form of radio transmission from WUSAT-3 in that time. Beyond that, WUSAT-3 must automatically begin to power up, complete its commissioning phase, and be prepared to start operations, listening out for a WUSAT-3 tag signal, etc. One of the first things that WUSAT-3 must do after power-up is to release another sort of antenna that is separate from the payload, but can transmit basic information about the condition of the satellite, and it can also receive some command signals from the ground. We would like this antenna to begin to transmit a basic heartbeat type signal, just so that we know it is safely in orbit and we can listen out for it. One of the most complex subsystems on WUSAT-3 is called the ADCS subsystem. During commissioning, its job is to detumble and stabilize the satellite, and then point the payload face of the satellite towards the nadir on the Earth's surface. It must try to retain that orientation throughout each orbit and also keep the satellite as stable as possible so that it is nice and steady when images are being taken and payload antenna data is being calculated. In order to receive and transmit to and from the various types of antenna on WUSAT-3 when it is in range, we will probably have a ground station, something like the one shown in this slide. This device is capable of rotating and elevating its dish and antenna mount in order to track the position of WUSAT-3 as it passes over, and to make sure the antennas are pointing directly at WUSAT-3 in order to receive and transmit the maximum signal strength possible. Depending where the ground station is sited, we may only have a window of about 10 minutes every 3 days in which to make successful transmissions to and from WUSAT-3. This slide isn't as complicated as it looks. If you look at any one of the white lines, it represents the ground track of where WUSAT-3 will pass over on a single orbit. However, because the Earth is rotating and WUSAT-3, like the ISS, will orbit about 16 times per day, then the Earth will keep moving east to west below the satellite, and hence the ground it passes over will keep changing. The mesh of white lines represents the changing ground track of WUSAT-3, and this repeats at approximately every 3 days. This is why a single ground station will only be within range once every 3 days. We are working with AMSAT UK to try to enlist the help of other radio operators with ground station facilities around the world, who can also listen out and receive data from WUSAT-3 that can be transferred to us. In terms of our wider WUSAT team, our main partner companies include Roke Manor Research, who have provided the concept and much technical assistance for the payload technology. Hardware providers include XCAM, who are providing a flight-tested camera for our payload system. RS Components, who have provided a large number of electrical and electronic components free of charge, Harwin, who provide high caliber interconnect systems, Eurocircuits, who provide printed circuit board manufacture. We also have links with software providers such as OpenCosmos, who give licenses and allow the use of their software for mission analysis, and WUSAT-3 TMS, who provide thermal modeling software. Also Low-Tech, who specialize in wildlife tagging technology and can advise on user needs, etc. We're also very grateful to Airbus, who carry out periodic reviews of our WUSAT-3 development and give highly valued advice on changes we might make. Our main engineering team comprises fourth-year Master of Engineering students who specialise in mechanical, electronics, systems, manufacturing and computer engineering. Each year they hand over to a new team. However, our team also includes every one of our company partners, many people at Warwick University and many others who we work with at various levels within the UK and Europe. We count anyone who is involved or interested as being part of the team. On this slide you can see the 2019-20 WUSAT team, including, sitting back right, myself and co-director Professor Julia Hunter-Anderson, who is a space systems engineer. Here we are presenting our WUSAT-3 mission to a panel of experts at the European Space Agency's Research and Development Centre, ESTEC, in the Netherlands in December 2019. I hope you've been able to grasp what we're trying to achieve with WUSAT-3 and the benefits it could bring. Here is a view from the ISS to finish. Thank you for listening.